everybody hear me okay? I think that we'll get started. It's 10:30. The other camps might join us here, but if not, we've got lots of other camps watching this live stream, and they're going to submit questions on Twitter. So I think we'll have a really good discussion about physics and gravity today. So as I introduced earlier, this is Dr. Jason Harlow, a lecturer in the Department of Physics at the University of Toronto. He's going to tell us a bit more about what he does with physics and answer our questions. But first, welcome Clinton to the call today. I understand this is your first time calling in, so hello to everyone. Welcome. And welcome to all of the camps that are watching the live stream. Good morning, everyone. I'll go to Dr. Harlow. Tell us a bit more about yourself, what you do, and a little bit more about like what is physics.
Okay, good. So my name's Jason Harlow. I'm sitting here in Toronto at the University of Toronto right now. This is my office, and it's in the physics department in the physics building. Physics is connected to astronomy, and that's actually one of the things I really love a lot. And I've done a lot of astronomy where I'm looking at stars in the galaxy that all orbit around sort of their common center of mass. And the sun is one of these stars. So I love the sun, and I love thinking about stars and where did the sun come from and how old is it? And these are the kinds of things that I studied for my PhD. And now what I spend most of my time doing is teaching physics. What is physics? Physics is the study of how things move and energy and forces and just how things work in the universe, what atoms are, how atoms build up to make
how things
actual things
move. And you sort of just cut off at the.
Okay, how things move, how things can have energy to move, forces can make things move, and what things are made of, like atoms, and how atoms can form to make bigger things like people or stars or galaxies, something like that. So that's basically what physics is, sort of the study of the most fundamental pieces of the universe and how things move around and work. And I actually have a demonstration here I can show you. Somebody else has joined us too. Hello.
Yes, I see that. Is that Brantford? Hi,
Brantford.
Hello,
You have a big lecture room, it looks like.
Yeah, they're at Wilfrid Laurier in Brantford.
Oh. Okay. Very good. So there's a campus of Wilfrid Laurier in Brantford? Okay. Things are a little glitchy, but I have this demonstration. Maybe I'll do that to show a little bit about circular motion and how it relates to orbits that deal with gravity. So, ready?
Excellent.
So
yeah.
All right. So what I've got, I'll just hold it up here. This is just a dish. I've also got an empty coffee cup. So what I'm going to do is I'm going to pour some water in the coffee cup. Whoops. Did not spill too much of it. Then I've got the dish on a string. I'm going to hold up the string and put the coffee cup on the string. And then I'm going to swing it over my head. Hopefully not spill anything. This might be a bit of a dangerous thing to do in the middle of my office because I don't want to make a huge mess. You ready?
Yeah.
Okay, I don't know if you saw that, but it went right around my head. There's still water in it. We do it one more time. These kind of things sort of depend on the video feed. Not a drop was spilled. Whoa. Okay. So there. Water over my head. Not a drop was spilled. Now I have a chalkboard just behind me which shows this idea of circular motion. So if you can imagine that some object, maybe the moon or maybe a marble or something is going around in a circle, it takes a force inward to keep it in that circular path. And if you were to take away the path or something, to take away that force, and it would just continue in a straight line. So, like if you're turning on a road, for example, and it's a curved road, but then you hit a big patch of ice, it'll just go straight on a straight line and end up in the ditch, even though the road curves around. It takes a force to keep it in. And that's what's going on with the string. The string is pulling a tension force towards the center of the circle, and that's pulling on the top, which is pulling the water, and preventing the water from going in a straight line and keeping it in a circle. And that's how orbits work. So when we send up a satellite into space, gravity actually pulls everything towards, if this is the Earth, it pulls everything towards the center of the Earth, and that's what keeps satellites in orbit. It's also what keeps the moon in orbit. That there's this constant tug of gravity always pulling it towards the center. Just the same way as the string pulls the cup towards it. That's my little physics gravity demo.
That was awesome. Who thought the spell? Anybody?
I beg nothing spilled. A little bit spilled, actually. Yeah. Not too much.
Oh, okay.
Mostly when I was pouring it, I just missed the cup.
Oh, you don't have to.
All right. So thank you for that demonstration. I'm going to go to our first question. Was there a question, Sudbury, for Dr. Jason Harlow today? Sudbury? Maybe not. Okay, how about Brantford? We'll go to Brantford just for a minute.
Caden has a question. Caden, come here.
So, what is the planet that has the most gravitational pull?
Well, I guess that would be Jupiter. It's by far the biggest planet. So it has mass, and mass is what provides gravity. So the most mass in the whole solar system is the sun, so that has the most gravity. And then the next most massive object is Jupiter. It's about 1,000 times less massive than the sun. But it's the problem with Jupiter is that it's not like the Earth. It doesn't have a solid surface, so you can't stand on it. It's just gas that gets more and more dense as you get closer and closer to the center. So I guess next up after that, the biggest rocky object in the solar system is actually the Earth.
We're being connected.
Okay.
Okay.
Was that Clinton joining back?
I still see Clinton.
Okay, Clinton. Clinton, did you have a question about physics or gravity?
Not hearing anything.
Hello.
Hello.
Hi, Clinton? Is that a camper in Clinton?
Yeah, hi.
Hi. I'm not sure if we just lost Clinton, but Dr. Harlow, can you still hear me?
I can hear you, and yes.
Oh, okay. I'm just going to go to a question from Twitter until maybe Clinton comes back on with us. They just screen.
Okay.
And maybe they're back. That's okay. Hi.
Hi, we're disconnected. Our question was, how was gravity discovered?
Well, I guess the first time somebody fell out of bed long, long ago, or a rock fell on some caveman's head, then I guess he must have discovered gravity right there. Some people say that Isaac Newton discovered gravity, who was English. But what he did is he was the first person to think about gravity and come up with a theory that gravity is not just something that pulls stuff down onto the surface of the Earth, but gravity attracts any two massive objects anywhere in the universe. So there's a universal force of gravity. So if I have even this mouse and this wallet, and they're near each other, they both have mass, so they're both attracting each other a little bit. Or if you're sitting there and your friend is sitting 5 feet away from you, you have a slight pull towards your friend of gravity. And so when you have two objects out in space, like the Earth here and the Moon here, they're both pulled towards each other a little bit, but the Earth is more massive, so it stays a little stationary while the Moon sort of orbits around it. So I guess the way Isaac Newton first came up with this, he was looking at the Moon and thinking about how there needed to be a force to keep it in its orbit. And he was looking at the Moon outside while he was eating his lunch under an apple tree, and an apple fell on his head and bumped him on the head. And he thought, hey, maybe the force that pulls the Moon is the same as the force that pulls the apple. I don't know if that story is true or not, but that's what they say. So. Isaac Newton, short answer.
Great. So I'll go to the question from Twitter from our camp in Ingersoll. Good morning, Ingersoll. They want to know what would happen if there was no gravity on Earth.
Well, everything would just float away. And in fact, the entire Earth would just turn into a whole lot of rocks that would float off into space. So that would not be good. And there's other effects of gravity. I mean, gravity is what's holding us down on the floor and allowing us not to accidentally, fall off the Earth. Gravity also is what keeps the Earth in orbit around the sun. So as I was saying, if something doesn't have a force pulling in a circular path, this orbit, it just goes off in a straight line at whatever velocity it had. So the sun stays at the same distance away from the Earth because of gravity. So if gravity went away, we would just travel away from the sun. The sun would get fainter and fainter, and then it all freeze to us sometimes. So gravity is a very lucky thing. And sometimes when you fall down and hurt yourself, and you're bleeding or something, you sort of curse gravity and say, I hate gravity! But you shouldn't hate gravity, because actually it's what's keeping us all alive. And it's also what keeps the air down on the Earth, too. And air is a good thing.
Okay, so this is sort of a related question from Dundas. They want to know if you could make gravity in space.
Yeah, there's something, so hi Dundas. I've heard about artificial gravity, which is the idea that the only one I've heard of that sort of works is that you have a spaceship that's like a can, and you rotate the can, and then everybody stands on the inner surface of the can, like the curve. So as it's rotating around, everyone feels like they're pulled towards the outside, and that gives them a feeling of gravity. So that's one way of kind of creating gravity when you're way out in deep space. So that's more something for science fiction, because I don't think anyone's ever built anything like that. These days, when people go up to space, they just live with weight, and when they come back to Earth, they have to sort of learn how to reuse their muscles again. Their muscles get weak from not having gravity. Another good reason for gravity is a good exercise.
Yes, that's a very good reason for gravity. Was there another question in Brantford? I see some campers patiently.
Yep. This is Nathan. He has a question.
How meteors get or formations of precious stones or stuff on them? Would they come from the planet? A piece broke off of the planet and then went into space?
You're talking about meteors? Your audio is cutting out a little bit.
Yes.
Yeah. Could you?
Yeah. No, I think I understood the question. So you're asking, I guess, where do meteors come from? Where do the precious minerals and stuff like that start, I guess, on meteors? So I guess when the whole solar system formed, there was a whole lot of all the different chemicals in sort of gas form way out in space. And where did that come from? Well, it came from a supernova explosion. So some nearby star generated all of these chemicals and then exploded and shot off all these chemicals and materials out into a huge, huge cloud in space. And then part of that cloud collapsed and became what is the solar system today. So the solar system includes, there's 8 planets, plus a whole lot of minor planets like asteroids or Pluto and that kind of thing. And a lot of little smaller things, which would be like meteors. And some of them get formed when 2 big minor planets will crash into each other and create a lot of debris, some of the smaller objects. But some of the smaller objects just were formed, 4.6 billion years ago when the whole solar system was formed from, what remained of that supernova long before that. And so they just orbit around the sun, and every once in a while, if they have an orbit that's very elliptical, they'll come close to the Earth, and then they can hit the Earth's atmosphere and actually fall down to the surface of the Earth. And then it's a meteorite, and you can pick it up and look at it. I don't hear your audio right now.
Very cool.
I hope that helped answer your question, Nathan. I can't hear you right now.
Yeah, I can't hear them either. Are you
The
on
audio
mute
problem, I can see you.
in Brentford?
Yes.
Oh, I heard you that time. I can see you the whole time, but I can't always hear you.
That was a good question, Nathan.
That's a good question.
Awesome.
All right. So our next question comes from our camp in Paris. Hello, Paris. Want to know, why does gravity down and not push up?
Yeah, that's a pretty good question. So Isaac Newton came up with this idea that all objects attract one another. So that's what the force of gravity just is. And why is that? Why is it an attractive force and not a repulsive force? I don't know. It just is. And I guess, maybe, maybe there's some things in physics that you just sort of have to accept. And one of these fundamental forces, like gravity, is an attractive force. We know there's other forces that do repel, like magnets can repel each other. The electric force, so force of electrons in each other, can also be repulsive, but not gravity. Gravity is always attractive. And so we're attracted to any nearby mass, and the nearest, largest mass is actually the Earth, and all these mountains and oceans and the iron core of the Earth and all that rock, most of it is below us, and very little of it is actually above us. Maybe a building that's higher than you or the ceiling or something, but most of the Earth is below you, and so we're attracted to the center of the Earth, sort of on average. And that's how when we say down, we mean towards the center of the Earth. And so if you were in Australia, you would actually be being pulled up, right? Because you're on the other side getting pulled towards it. But you would just call that down. So, and they think we're upside down. So,
Yeah. Good question, Paris. Is there one more question in Brantford we can go to? We're coming to the end of our time with Dr. Harlow, but we have time for one more in Brantford. Hi.
audio.
Yeah, we can't hear you. You might be on mute. Brantford, are you on mute? We can't hear. I'm sorry.
I cannot hear you.
Only a little bit. Maybe come a little closer to the mic.
Come closer.
That's better.
Why is there only gravity on Earth and not?
So,
Why is the gravity pull on Earth not as strong as on the other planets?
yeah, it was very quiet.
Does gravity
Could
on
you
Earth
repeat the question,
not
please?
as strong?
Why is the gravity pull on Earth stronger than the gravity pull on other planets?
Okay, so yeah, why is the gravity pull of Earth stronger than it is from other planets? I think so. So this is a big part of physics, is studying gravity and how it works. And there's 2 factors that affect the strength of gravity. One is the mass of the object. So like something that's small, like your bicycle or something like that, only has a very, very weak gravity force attracted to it. Whereas something big, like the sun or the earth or something, has a much stronger gravity. And the second part to it is distance. So something that's very, very far away, even if it's huge, will have a small gravity effect. So the Earth is the closest, biggest thing to us, and that's why it has by far the strongest gravity pull on us. But even the Moon has a pretty big gravity force as well, and so does the Sun. And so the combination pull of the Moon and the Sun is what causes tides to go up and down in the ocean. So there's a weaker pull there. So the water's pulled towards the center of the Earth by the Earth, but it's also pulled a little bit out towards the Moon, and a little bit towards the Sun. And as the Earth rotates, you get the effect of tides going up and down. It's mass and distance are the two main parts to that. I didn't catch your name either.
Great. Thank you.
It was good to meet you.
Yeah, no, I didn't catch his name. But thank you for your question.
My name is Huxley.
Huxley?
My name is Huxley.
Hey, good to meet you.
Thank you.
That was a good question.
Thank you very
Bye.
much. Bye. So unfortunately, that's all the time for our question and answer session with Dr. Harlow. Thank you so much, Dr. Harlow, and for your patience in trying to hear all the campers' questions and everything. Thank you very much. And thank you, Branford, for joining, and Clinton as well, even though we lost them, but we'll see them next week, I'm sure. Thank you.
Bye-bye. Bye, Branford. Have a great rest of your day.